welcome to this problem walkthrough. Today, we'll be diving into problem number 2061, titled Number of Spaceships. Throughout this video, we'll explore the problem statement, consider different approaches, and break down the solution step by step. Let's get started. In this problem, you're tasked with determining the number of valid spaceships that can be formed from a given string text and a list of patterns. Each spaceship is represented as a string, and it's valid only if it can be formed by rearranging the letters in text without exceeding their frequency, and it exactly matches one of the strings in the patterns list. The input includes the string text, which can be up to 10,000 characters long, and a list of up to 100 patterns, where each pattern can be up to 100 characters. Your goal is to return an integer representing the total number of valid spaceships that can be formed. This involves carefully using the available letters in text and ensuring that each formed spaceship adheres to the given constraints. Let's look at the first example. Here, the input string text is APCAP, and the patterns are ABC, CA, CAB. The letters in text are APCAP, which means each letter A, B, and C appears twice. From this, you can form one ABC spaceship and one CA spaceship. However, there are no remaining letters to form another valid spaceship. The total number of valid spaceships formed is 2. This demonstrates how the letter frequencies in text determine how many spaceships can be created. Now, in the second example, text is AAA, and the patterns are AA, AAA, AAA. The string text has 4 characters. Using these, you can form 2 AA spaceships and 1 AAA spaceship. Additionally, it's possible to form 1 AAA spaceship. However, since the letters in text are exhausted after this, no more spaceships can be created. The total count of valid spaceships here is 3, showing how different patterns can utilize the same pool of letters in text without exceeding their frequencies. In the third example, text is XYZ, and the patterns are ABC, DEF, GHI. The letters in text are X, Y, and Z, none of which match any of the patterns. Since none of the patterns can be formed using the given letters, the total number of valid spaceships is 0. This highlights that if the letters in text don't overlap with the letters in the patterns, no valid spaceships can be created. Now, let's consider the constraints and edge cases. The length of text can be up to 10,000, so your solution needs to handle large inputs efficiently. If text is shorter than any pattern in patterns, it's impossible to form that spaceship, and you should return 0. Similarly, if patterns is empty, you return 0, as there are no spaceships to form. One interesting edge case is when text in all patterns consist of the same letter, like text equals AAA and patterns equals AA, AAA. Here, the solution must carefully count how many of each spaceship can be formed without exceeding the frequency of letters in text. Ensuring accuracy in these computations is key to solving the problem correctly. Let's start by discussing 2 possible approaches to solve the problem. First, the brute force approach. The intuition here is to generate all possible permutations of the string text and then check which of these permutations are valid spaceships by comparing them to the strings in the patterns list. While this method is straightforward to understand, it quickly becomes impractical for large inputs due to the sheer number of permutations involved. For a string of length n, there are n permutations, and checking each one against the patterns list makes this approach computationally expensive, with a time complexity of O(n)(m). Now, an alternative is the frequency matching approach. Instead of generating permutations, we focus on the fact that a valid spaceship can be identified by matching the frequency of characters in a substring of text to the frequency of characters in any string from patterns. This approach is more efficient because it avoids the factorial growth of permutations. By using hash maps or dictionaries to store frequency data, and applying a sliding window technique to check substrings, we achieve a significant reduction in computational complexity, down to O(n)(k), where k is the maximum length of strings in patterns. However, this approach does require additional space for the frequency maps, highlighting a trade-off between space and computation time. Building on the frequency matching approach, we can introduce an optimized sliding window technique to further enhance efficiency. The key improvement here is maintaining a dynamic frequency count as the window slides across the string text. Instead of recalculating the frequency map for every window, we simply update the counts for the characters added to or removed from the window. This greatly reduces redundant computations. The steps are straightforward. First, pre-compute the frequency maps for the patterns. Then, initialize a sliding window on text and maintain its frequency map dynamically. For every character added to the window, increase its count in the frequency map, and for every character removed, decrease its count. This ensures that the frequency map is always up to date with minimal computation. Finally, compare the updated frequency map with the pre-computed maps for patterns to identify matches. This optimization improves the time complexity to O, n plus m asterisk k, where n is the length of text, m is the number of patterns, and k is the average length of the patterns. The sliding window approach with dynamic frequency updates stands out as the most effective strategy for solving this problem. It provides a great balance between efficiency and implementation complexity. By focusing on matching letter frequencies, we eliminate the need to generate exact permutations, which is computationally prohibitive. The dynamic sliding window efficiently adjusts frequency counts as it moves through the string, avoiding redundant recomputation. Pre-computing frequency maps for the patterns ensures that comparisons can be done in constant time, further boosting performance. These optimizations make the approach both elegant and scalable. However, there are some trade-offs to consider. The space complexity increases slightly due to the need for frequency maps, and the dynamic update mechanism introduces a level of complexity beyond simpler methods. Still, this trade-off is worthwhile because of the significant performance gains achieved. The brute force method, while conceptually simple, is not a viable option due to its factorial time complexity. The rapid growth in permutations makes it infeasible even for moderately sized inputs. Additionally, the naive approach does not scale well with either the length of text or the size of the patterns list. In contrast, the sliding window approach with dynamic frequency updates is both time and space efficient. The final time complexity of O, n plus m asterisk k, ensures that the algorithm can handle larger inputs gracefully, and the space complexity of O, k plus 26, is reasonable, where 26 accounts for the number of lowercase English letters. Overall, this strategy offers the best balance of efficiency, scalability, and practicality, making it the optimal choice for solving the problem effectively. To tackle this problem, the goal is to determine which permutations of the given string, text, match any of the strings in the provided patterns list. The brute force algorithm for solving this involves two main steps. First, we generate all possible permutations of the string text. This can be done using a backtracking approach, which systematically explores every possible arrangement of the characters. For instance, with a string like ABC, the permutations would include ABC, ACB, BAC, CA, CAB, and CBA. Since there are n permutations for a string of length n, this step becomes computationally heavy as the length of the string grows. Once we have all the permutations, the next step is to compare each one against the patterns list. For every permutation, we iterate through the list of patterns to check for an exact match. This ensures that no potential match is overlooked, but it also adds another layer of computational effort. After generating the permutations and comparing them to the patterns list, the next step is to store any valid matches we find. These matches can be stored in a results list or, even better, a set to ensure we avoid duplicates. The process continues until all permutations have been checked. Finally, we return the results list, which contains all the valid matches. If no matches are found, we simply return an empty list. However, this brute force approach comes with significant inefficiencies. For instance, generating all permutations is highly computationally expensive, especially for longer strings. A string of length 10 would require generating 10 factorial permutations, which is over 3.6 million combinations. Moreover, comparing each permutation against the patterns list adds further overhead, with a time complexity of O, n. *m, where n is the length of the string and m is the number of patterns. Additionally, storing all permutations in memory can lead to high space usage, although this can be mitigated by generating permutations on the fly using a generator. To implement the algorithm effectively, we need to use appropriate data structures. A list or generator can be used to handle the permutations, but a generator is preferred for large inputs to minimize memory usage. For storing valid matches, a set is an excellent choice because it automatically eliminates duplicates and allows for fast lookups. The patterns list can remain as is, enabling straightforward comparisons.
To optimize the algorithm, we can introduce several improvements.
For example, we can prune permutations early. If a partial permutation cannot possibly match any pattern, we can skip generating further permutations from that branch. Additionally, converting the patterns list into a hash set allows for O1 lookups, significantly reducing comparison time.
Another important optimization is to avoid generating all permutations outright.
Instead, we can use dynamic programming or other combinatorial techniques to generate only the subsets or sequences that are likely to lead to valid matches.
There are a few critical edge cases to consider when implementing this algorithm.
If the input string text is empty, there are no permutations to generate, so we should return an empty list. Similarly, if the patterns list is empty, there are no valid patterns to match, so the result should also be an empty list. When the input string contains duplicate characters, the algorithm must ensure that permutations are handled correctly and do not produce redundant results.
Lastly, if no permutations match any pattern in the list, we should return an empty list to indicate that no valid matches were found.
In terms of complexity analysis, the time complexity of this algorithm is dominated by the permutation generation step, which is O(n). Comparing each permutation against m patterns adds another factor of O(m), leading to an overall complexity of O(n).
*m.
The space complexity depends on how permutations are managed. Storing all permutations requires O(n) space, but using a generator reduces this to O(n), which accounts for the stack space used during recursive generation. This Python implementation solves the problem by first counting the frequency of characters in the input string text using the counter class from the collections module. This provides a quick way to determine how many of each character are available in the text. For each string in the patterns list, the function counts the frequency of characters in the pattern using another counter. It then checks if the pattern can be formed from the text by comparing the character counts. Specifically, for each character in the pattern, it ensures that the count in the text is greater than or equal to the count in the pattern. If this condition is satisfied for all characters in the pattern, it increments the result counter. Finally, the function returns the total count of patterns that can be formed from the text. This approach ensures efficiency by avoiding the need to generate all permutations explicitly, focusing instead on character frequency comparisons. Here, we start by importing the necessary libraries and defining our class, solution. The main method of interest is number Spaceships, which takes two inputs, a string text and an array of patterns. Our goal is to determine how many of these patterns can be formed using the characters in the given text. To achieve this, we first calculate the frequency of each character in the text using a hash map. This allows us to efficiently store and retrieve the count of each character. Next, we initialize a variable, result, to 0. This will keep track of the number of patterns that can be successfully formed. For each pattern in the patterns array, we compute the frequency of its characters in a similar way, using another hash map. This helps us compare the availability of characters in the text with the requirements of the current pattern. To perform this comparison, we introduce a Boolean variable, canForm, and assume it's true by default. We then iterate through the required characters in the pattern, checking if the text provides enough occurrences of each character. If at any point a character is insufficient, we set canForm to false and break out of the loop. After checking all the required characters for the current pattern, we evaluate the canForm flag. If it remains true, it means the pattern can be formed using the characters in the text, so we increment the result counter. This process repeats for each pattern in the array, ensuring that we evaluate all possibilities. Finally, after processing all patterns, we return the result, which represents the total number of patterns that can be formed. This implementation effectively combines character frequency counting and validation checks to solve the problem efficiently, leveraging the power of hashmap to handle character frequencies in both the text and the patterns. To begin solving this problem, we start with a basic example. The input text is spaceship, and the patterns we want to check are ship, space, and ace. First, we initialize our variables. Text_count is a frequency count of all the letters in the input text, so we can see that S and P appear twice, while other letters like a, C, E, H, and I appear just once. We also initialize result to 0, which will keep track of how many patterns can be formed using the letters in the text. Next,
we process the first pattern, ship. We calculate the frequency count for this pattern, which shows that each letter in ship appears exactly once. Now, we check each letter in the pattern to see if it exists in text_count with at least the required frequency. For S, H, I, and P, this condition holds true. Since all checks pass, we increment result to 1, indicating that this pattern can be formed from the text. Now we move on to the second pattern, space. The frequency count of this pattern shows that each letter S, P, A, C, and E appears once. We then verify if the text contains each of these letters with sufficient frequency. For S, P, A, C, and E, the condition is satisfied in all cases. Since the text can form this pattern, we increment result to 2. Next, we process the third pattern, ace. The frequency count for ace is straightforward, with each letter appearing once. Again, we confirm that the text has the required frequency for each letter, A, C, and E. All checks succeed, so we increment result to 3. At the end of this example, the final output is 3, meaning all 3 patterns are valid. Now let's consider an edge case where the text doesn't contain enough characters to form some of the patterns. The input text is ABC, and the patterns are ABCD, UB, and BC. First, we initialize text_count to store the frequency of each letter in the text. A, B, and C each appear once. We also set result to 0. For the first pattern, ABCD, the frequency count shows that A, B, C, and D each appear once. Checking these against the text, we see that A, B, and C meet the required frequency, but D does not exist in the text. Since this check fails, result remains 0. Next, we process the second pattern, UB. The frequency count shows that both A and B appear once. Checking these against the text, we find that both letters meet the required frequency. Since the text can form this pattern, we increment result to 1. Then, we look at the third pattern, BC. The frequency count for BC indicates that both B and C appear once. Verifying these letters in the text, we see that both meet the required frequency. As a result, we increment result to 2. At the end of this example, the final output is 2, meaning only 2 of the 3 patterns can be formed from the text. In this example, we examine a scenario where no patterns can be formed from the text. The input text is XYZ, and the patterns are ABC and DEF. First, we initialize text_count to reflect the frequency of each letter in the text. X, Y, and Z each appear once. We also set result to 0. For the first pattern, ABC, the frequency count shows that A, B, and C each appear once. Checking these letters against the text, we see that it is not present in the text. Since this check fails, result remains 0. For the second pattern, DEF, the frequency count indicates that D, E, and F each appear once. Checking these letters against the text, we find that D is not present in the text. Since this check also fails, result remains 0. At the end of this example, the final output is 0, as none of the patterns can be formed using the letters in the text. To analyze the time complexity of the number spaceships function, we begin by breaking it into components. First, we have the operation of counting characters in the input string text. The counter function iterates through all characters in the string and counts their occurrences, leading to a time complexity of O, M, where M is the length of text. Next, we consider iterating through the list of patterns. If there are P patterns and the average length of a pattern is K, we perform 2 main operations for each pattern. The first is counting characters in the pattern itself using counter, which takes O, K, time, as it depends on the length of the pattern. The second is the feasibility check, where we compare character counts between the pattern and the text. For at most K unique characters in the pattern, this involves a lookup and comparison, which also takes O, K. Combining these 2 operations for one pattern gives O, K, plus O, K, equals O, K. Since there are P patterns, the total work for this part is O, P asterisk K. Now, let's consider the result accumulation step. Updating the result variable is a simple operation that takes constant time, or O1, and does not contribute to the overall time complexity. When we combine all the components, we have O, M, for counting characters in text and O, P asterisk K, for iterating through the patterns.
Therefore, the overall time complexity of the function is O m plus p asterisk k. This demonstrates how the algorithm efficiently balances the cost of processing the input in patterns while keeping the operations linear with respect to their lengths. Turning to space complexity, we analyze the auxiliary space used by the algorithm. First, the counter for the input text requires U space, where U is the number of unique characters in text. In the worst case, if text consists only of lowercase English letters, U is capped at 26. Next, for each pattern, we create a counter, which requires V space, where V is the number of unique characters in the pattern. Similarly, V is capped at 26 if the pattern only contains lowercase letters. However, since we discard the counter for each pattern after processing it, we do not accumulate space for all patterns. Finally, the result variable is a simple integer, requiring only O1 space. These components show that the space requirements are proportional to the number of unique characters in text and the current pattern being processed. When combining the space requirements, the total space complexity is dominated by the larger of the space used for text_count and pattern_count. This results in an overall space complexity of U plus V, where U and V are the number of unique characters in text and the current pattern, respectively. In the worst case, when both are restricted to lowercase English letters, this simplifies to 26 plus 26, which is 1. Comparing this approach to a brute force or naive method, we see significant efficiency gains. A naive method would involve generating all permutations of text to check for pattern matches, which has a prohibitive time complexity of m. Instead, by using frequency counting and direct comparison, this algorithm avoids exponential complexity and achieves a much more efficient m plus p asterisk k time complexity. This demonstrates the power of leveraging optimized data structures like counter to reduce both time and space costs. Finally, let's consider the best, average, and worst cases for the algorithm. In the best case, all patterns can be formed using only the first few characters of text. While the constant factors may be smaller due to early termination of checks, the overall complexity remains m plus p asterisk k. In the worst case, all patterns must be fully checked against text, but the asymptotic complexity still remains m plus p asterisk k. This consistency arises because the algorithm always processes the entire text and all patterns, ensuring that the time complexity is stable regardless of input. Mathematically, the algorithm processes the text once for counting character frequencies, which is m. For each of the p patterns, it processes the pattern length and performs comparisons, both of which are k, leading to p asterisk k. Combining these gives m plus p asterisk k as the time complexity. The space usage, dominated by the counters, is 1 for fixed alphabets like lowercase English letters. These proofs confirm the efficiency and scalability of the algorithm across different scenarios. When solving this problem, there are a few common mistakes to watch out for. First, not handling edge cases, such as empty strings or an empty list of patterns, can result in runtime errors or incorrect outputs. These situations often require explicit handling, like returning early or defining default outputs. An empty input, for instance, should produce no valid spaceships. Next, inefficient permutation generation is another frequent issue. If you generate all possible permutations without pruning invalid branches early, the computation can become unnecessarily expensive. This is particularly problematic because generating permutations has a factorial time complexity, and pruning can significantly reduce this overhead. Finally, some solutions fail because of a misunderstanding of the problem's constraints. For example, overlooking the maximum length of the input text or the number of patterns can lead to algorithms that fail under stress tests. A robust solution must include careful constraint analysis to ensure scalability and efficiency. Another common mistake arises from incorrect pattern matching logic. Many assume that simple substring checks are sufficient, but the problem may require exact matches or a specific ordering of characters. This kind of misalignment in logic can lead to false positives or negatives, causing the solution to fail crucial test cases. Additionally, ignoring case sensitivity or character repeats can be a significant oversight. For example, strings with duplicate characters, like AA, or mixed case inputs need special attention to ensure no valid configurations are missed or duplicated. Neglecting these details often results in incomplete or incorrect solutions, so it's essential to account for all edge cases, including those involving repetitive or mixed case strings. In interviews, this problem type offers several opportunities to demonstrate your skills. Recognizing patterns in the problem is key. Many tasks involving permutations or matching can be optimized using techniques like backtracking or memoization. Interviewers often look for candidates who can move from a naive solution to a more efficient one. It's also important to ask clarifying questions during the problem discussion. For example, does the problem require exact matches, substrings, or a specific ordering of characters? Misunderstanding these requirements can lead to wasted effort. Furthermore, understanding complexity is critical. Brute force solutions are rarely acceptable for medium or hard problems, so you should be prepared to discuss trade-offs in time and space complexity. Lastly, a solid testing strategy is essential. Make sure to highlight how you would test your solution, particularly for edge cases like empty inputs, single character strings, and patterns with repetitive elements. To solidify your understanding of this problem, it's helpful to explore related problems on LeetCode. For example, LeetCode 46 focuses on generating all permutations of an array, which is a foundational concept for this type of problem. LeetCode 47 builds on this by introducing the handling of duplicate elements in permutations, a skill directly applicable to ensuring unique solutions. LeetCode 10 tackles regular expression matching, which parallels the idea of validating spaceships based on specific patterns. Finally, LeetCode 784 delves into letter case permutation, offering insights into managing case variations in pattern matching. These problems help reinforce the key concepts and edge cases you'll encounter in similar challenges. There are several alternative approaches you can consider for solving this problem. One is backtracking with pruning, where you generate candidate solutions and discard invalid paths as early as possible. This approach reduces computation, though the worst-case scenario may still involve exponential complexity. Another option is dynamic programming, which uses memoization to store intermediate results and avoid redundant calculations. While efficient, this method can be complex to implement and requires additional memory for caching. Lastly, you could use a tree-based matching approach by building a tree from the patterns list and validating permutations through a traversal of the tree. This method is particularly efficient for large pattern sets but may require significant pre-processing time and memory to construct the tree. Each of these methods has its trade-offs, and the best choice depends on the specific constraints and requirements of the problem. Great job reaching the end of this problem solution. We covered the key approaches, discussed the complexities, and highlighted important takeaways you can apply to similar challenges. Thanks for watching, and be sure to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!